Good afternoon, everyone. My name is Venkatesh Ramanathan. I'm a senior data scientist at PayPal. I currently work on various research efforts on fraud detection. Prior to that, I have done research applying machine learning and NLP for other domains, which includes face recognition, anti-spam, and phishing detection. I also have many years of software engineering experience building distributed systems. Today, I'm going to be talking about collusion detection using Spark. How do I go to the next slide? Sorry. Okay, this is an outline of my presentation. So I'll briefly talk about PayPal and what we do at PayPal. Then I'll address how we are tackling fraudsters at PayPal. I'll talk about specific type of fraud called collusion fraud. Then I will present the solution I came up with to address collusion fraud. I'll share some early results from some of my experiments and conclude with a summary of what I have learned so far. PayPal, consumers love PayPal because of its simplicity, security, and flexibility. It's very easy to create an account, and with one account, you will be able to pay both online and offline in stores, as well as you can send money payment to your family and friends. PayPal offers buyer protection, so buyers can have a worry-free buying experience. In addition, it's very flexible, so you can use on most of the devices on PayPal in over 200 markets. Merchants also love PayPal because of its global reach. PayPal is available in over 200 markets, and it's also, we have more than 165 million active user accounts. PayPal also provides a platform for merchants to manage their businesses much more efficiently. The product which you see here is PayPal Here, which the merchants can plug into the device and collect payments from the consumers very easily. PayPal have significant market advantages over its competitors because of its 15 years of experience. One of the key differentiators that PayPal has is state-of-the-art fraud detection and risk management systems. So how do we address fraudsters at PayPal? We have state-of-the-art feature engineering, machine learning, and statistical models to detect fraud patterns and prevent them. We also have a highly scalable and multi-tiered software architecture to detect and prevent fraud. We have a superior team of data scientists, financial analysts, intelligent analysts as well. PayPal, as I mentioned, we have a multi-tiered software architecture. At the transaction level, when a payment goes through, we have a sophisticated machine learning and statistical models to detect fraud. Also we have even more sophisticated algorithms we apply after the transaction is complete, so we'll be able to even reverse transactions, fraudulent transactions. At the account level, we monitor various activities. Some of the activities, for example, could include frequent payments or profile changes. Somebody tried to make a payment or purchase some item a few minutes back and change their address to, from US to Australia could potentially trigger our fraud detection system. We also have network level monitoring where we see if somebody is sending a lot of payments from majority of the accounts to a single account, that could potentially be a money laundering activity. So we have systems and algorithms and models to detect those kind of patterns. Fraudsters are becoming increasingly smarter and adaptive. So we have to be always few steps ahead of them to, so we have state-of-the-art machine learning algorithms. So we also always looking for improving our state-of-the-art. So one such fraud is actually the collusion fraud. So what is collusion fraud? Let me walk you through an example. Buyer purchases an item using PayPal from a merchant. Seller ships the item to the buyer. Buyer finds box empty and claims the box is empty and asks PayPal for a refund. Because PayPal has a buyer protection, we refund the buyer. The PayPal asks seller for proof. The seller provides proof such as when the particular item was shipped. Because we also offer seller protection, PayPal credits the merchant account with the transaction amount. The net result is a loss to PayPal. Now imagine that these buyer and seller split the money. That is an example of a collusion fraud. So what if there are many such buyers and many such sellers colluding with each other, is resulting in a significant loss to PayPal? What if such buyers always stay below the radar, buyers and sellers stay below the radar to avoid being caught by our some other detection system? What if such sellers behave well with majority of the buyers and collude with very few? How do we detect if the buyers and sellers are legitimate or if they are colluding with each other? A solution is one possible solution to handle that is using collaborative filtering. So most people are familiar with movie recommendation where collaborative filtering is widely applied. For example, the rows of the matrix represent, users represent the rows of the matrix, and the columns represent the movies. And in this particular example, you can see user 1 and user 3 have similar taste. So when we want to recommend, because of the similarity, we can recommend movie C to user 1 because the user 1 is very similar to user 3. Similarly, we can apply collaborative filtering for collusion fraud, where the rows of the matrix could represent the buyers, and the columns could represent the sellers, and the cells could represent whether they are colluding or not. In this particular example, for example, buyer 1 and buyer 3 have very similar fraud patterns. You can see that whenever buyer 1 and buyer 3 interacts with the seller B, it always results in a fraud. So thus, when buyer 3 transacts with the seller D, we can potentially conclude this seller D is also part of the fraud ring. We could apply the rows of the matrix doesn't always have to be buyer IDs. For example, buyer could create multiple identities, right? So the rows of the matrix, in that case, we could use the IP address. Similarly, the sellers could be IP address instead of the identifiers itself. So there are several other ways we can represent to solve the same problem. So you could, for example, buyer could also hop from multiple IP addresses, or we could, in that case, we could use a region as the rows of the matrix, so we can detect if there is money laundering activities going on within between specific regions of where we operate. Then the cells of the matrix doesn't have to always be fraud or not fraud. It can be percentage of bad transactions. It could it could also be how much loss we suffered between those respective buyer and seller. So there are several challenges for applying collaborative filtering for collusion fraud. For example, fraud is never explicit. Attacker is not going to say, I am committing a fraud, unlike a movie example. And fraud patterns are quite complex, actually. Attackers have always, it's quite complex and dynamic in the sense that they always change their patterns to avoid getting caught by our fraud detection system. And seller and buyer patterns are quite different. For example, seller is selling it and buyer is buying it, so their patterns are quite different. So this is my proposed architecture. We build a buyer fraud model which intimately models the specific patterns the buyer goes through when transacting with the PayPal. And we build a seller fraud model which models the seller transactions at the first stage. And we combine the prediction of buyer and the seller fraud model to build a collusion fraud model. So this two-stage approach helps with not only not throwing the entire buyers and sellers into a gigantic matrix for using for collusion fraud. Instead, we can model the individual patterns intimately, then use that output of this prediction to see whether they are actually colluding with each other. So my proposed architectures for buyer model, fraud model, I use deep learning. I'll go about why I picked deep learning for buyer and seller fraud models, and use the prediction of deep learning network to build collusion fraud model using matrix factorization. So in this case, the matrix, the buyers and sellers, and the tags are obviously implicit instead of explicit, unlike a movie scenario. So why did I choose deep learning? First of all, deep learning is a deeper neural network helps to model the complex patterns that fraudsters constantly switch from one place to other place and to avoid getting caught. Because deep learning is inherently captures some of the nonlinear nonlinear effects as part of any fraudulent transactions. We have been applying some variation of deep network for many years. That is one of the main reasons why our fraud detection system was extremely superior. So I wanted to see whether a deeper network can help with some of the fraud detection. Also, we have a state-of-the-art feature engineering group where some of the nonlinearity is captured at the feature level. So I wanted to see whether a deeper network can help to offset some of those feature engineering efforts so that we can detect frauds quicker and sooner than our existing models. It also has been widely been successful of late for various image and object recognition. So when we want to detect multiple fraud patterns in the same type of transactions, a deeper network could potentially help with that, determining that. The tool I used is H2O. Actually, I think they have a shop set up here at the Hadoop conference. They have a highly scalable implementation of deep learning. Basically, they have a feed-forward neural network architecture. It's part of that H2O tool, and more importantly, it's open source, so anybody can try it. Obviously, because of the scale of the data we are looking for, we always want a scalable architecture where we can scale out with just by adding additional nodes to the existing cloud. It also works seamlessly with the other data, big data frameworks. For example, they have an integration with the Spark, and we can pull the data from HDFS. This is where most of our data sources are. This is the architecture of deep learning network. So you can certainly talk to the H2O team to better understand it. Essentially, you split the entire data set across your cloud, and they have a pseudo map reduce phase. In the map phase, they compute a gradient on a subset of the data, and the reduce phase, they exchange those information to recompute the weights. And that continues for several iterations of a neural network until it converges. They also have a grid search parameter where you can say, I want to vary these number of neurons and the number of layers in this space. So they search through the space to build models across this entire search space, so which you can, basically, instead of you having to do manually, they do automatically behind the scene for you. For the collusion fraud model, I used matrix factorization. Essentially, the way matrix factorization, for people who are not familiar with it, the way it works is that our collusion fraud model, which I built, is actually between buyer and seller, and the matrix is actually a fraud matrix. Essentially, you break those fraud matrix into a lower dimensional factor matrices. So in the lower dimensional space, is much more effective, and it is more importantly, the matrix factorization implementation in Spark is parallelizable. With the scale of data we are working, it's extremely essential component for us to even apply matrix factorization. So the implementation, the way the optimization algorithm is implemented in Spark uses ALS called alternating least squares. Basically, you initialize the buyer and the user vector, feature vectors randomly. The reason it's alternate is alternate between the item vectors, in this case seller, the buyer, or the seller item is a seller and the user is a buyer vector. So alternate between this until it converges. For the experiment, I started with a gigantic data set, but as with any data mining tasks, you spend a lot of time in data preparation and before you can get to the actual building model process. So I was getting close to the conference. So I have to downsample it significantly to see whether this particular architecture I had in mind is even useful. So this is a very small subset of the data set. We have millions of buyers and thousands of merchants in this data set. I use 60% of the data for building the model and the remaining 20% for validation and the remaining 20% for testing. A cluster is actually, we have several clusters for production, development, QA, and all types of clusters where we have thousands of nodes. This particular experiment I performed in a very small R&D cluster, which has got 48 nodes. The reason is that this cluster is newly set up, so I could make use of the latest version of HTTP 2.x, which has got Spark nicely integrated. So my initial efforts was, when it is not something is nicely integrated, you spend a lot of time trying to put everything together. The HTTP 2.x made it seamless to see whether matrix factorization work for our particular case. This is my cloud setup. Basically, all our data is in HDFS, so we had to do a lot of big MapReduce jobs to prepare the data and pre-process the data and sanitize the data upfront as with any data mining task. The H2O cloud basically sucked in the data. So H2 is actually in-memory processor, just like Spark. So all the computation happens in memory. So but the data is actually persistent in HDFS. And H2O has a very nice interface, R interface. They also have Python and REST API to interact with them. I use the R interface to build my deep learning buyer and seller models. So for the matrix factorization, I used the Spark release available with HTTP 2.x. So and it's basically a Scala client running MapReduce jobs, Spark jobs within the Yarn framework. So these are the results from my deep learning experiment. I did several work, and you can look it up in my other presentations, but what I wanted to show was that here, the question which I wanted to answer was, can I get deeper network basically helps with performance. So you can see that the number of hidden layers vary from 2 through 8 layers. For 200 neurons at each layer, you can see that I got a lift of about 7% improvement in performance. The performance metric is basically the area under the ROC curve, which is a well-known metric in the data mining community to see whether how good your model is. But this is actually consistent with this various other research efforts applying deep learning to other domains as well. So you can see that you don't have to have a deeper network. You don't have to have a layers more than 8 or 10. You can see that the performance saturates. But a deeper network does help, but you don't have to have a too deep a network to get good performance. In terms of, this is a result, actually, what I wanted to know was that we spend a lot of time in feature engineering. We have a superior team of data scientists to come up with very intelligent features. That is, I wanted to see, can a deeper network help with some of those feature engineering efforts? So in this particular data set, I had 1,500 features. So instead of using all the 1,500 features, I selected a subset of 500 features, and I trained a deeper network just by having more layers and more neurons. Deep learning was able to give about 11% improvement in performance, which shows that a deeper network can help with detecting frauds. Basically, we can do more with less number of features. So this is actually preliminary experiment results from my collaborative filtering task. So as you can recall that basically my collusion model is predictive. I use the predict tag of buyer and seller models. If both of them are fraud or if either of them are fraud is considered a fraud. So I use that to build my matrix factorization model using ALS. So you can see in this particular case, it is these particular transactions between this particular buyer and the seller. Deep network model was unable to catch it. Doesn't mean the deep network is bad, but this is actually wasn't able to because the deep buyer and the seller model are focused on the specific patterns of the buyer and seller. It was unable to catch that. But matrix factorization using ALS was able to catch this fraud much earlier. So you can see this particular buyer and seller always being transacting an amount less than a particular threshold, and it basically went on for about 21 transactions and resulted in a net loss of 1,700. The collusion model which I built was able to catch this fraudster. So this is actually a small example, but I'm continuing with this experiment. So, in summary, actually, deep learning model is really good for detecting frauds, both buyer and the seller fraud. Just to set the expectation, most of these experiments are done offline, so there are always challenges of applying any type of models to online. So that is it's a continuing effort we are trying to do. The matrix factor model shows promise. Actually, definitely was able to capture interaction between buyer and seller to detect collusion fraud. So basically, we can detect a community of fraudsters. A fraud ring goes on between buyer and seller. It can also be extended to, for example, I picked buyer versus seller for money laundering activities. People move money from between two accounts, and they don't have to have a business, right? So it can be extended to user-to-user interaction. Matrix factorization can be applied. Finally, acknowledgements. Actually, definitely I want to thank Hortonworks. They have an incredible support team, and also more importantly, they embrace open source on making this platform available for most of my experiments. A team at H2O contacted several of those team members to support some of my deep learning experiments. They have a very good support team who help with some of my deep learning models. And finally, more importantly, the approval team at PayPal, they worked tirelessly to get some of my presentation slides ready for this presentation. So thank you, everyone. So actually, at this point, I cannot take any questions, but I will be very happy to answer your questions. My email address is on the conference website. You can contact me via email. I'll be happy to get back to you. And thank you for attending.